Okay, in this video, we're going to discuss some interesting steady state results as well as some decisions that you need to make when you're designing a queuing system. So thinking about what are some of the control parameters or decision variables that we have to monkey with, and how do they affect the queue metrics? Okay. So I'll present some results for steady state in a one server MM1 system. So this has exponential arrival and service times and just a single server. Provided the utilization rate, which is the arrival rate divided by the service rate, is less than 1. If you have more arrivals on average than services, then your system's going to blow up. Okay, or just kind of your queue is going to get longer, longer, longer. It's never going to reach steady state. But if it's less than 1, then the probability that there's n people in your system is 1 minus rho times rho to the n. And so the probability that nobody's in your system, so n equals 0, is just going to be 1 minus your utilization rate. So if your utilization rate is a half, then actually the probability that nobody's in the system is 1 minus a half, which is a half. But if your utilization rate is 90%, then the probability that nobody's in your system at a given time is 10%. Okay, so that's another way of kind of thinking about what rho represents. L is the number of people in the system as a whole, is going to be rho over 1 minus rho. And so, for example, if rho is 90%, it's going to be 90 over 1 minus 90%, or 0.9, would be 0.9 over 0.1, or 9 people on average. Okay, you can also kind of plug in what rho is, and it ends up being lambda over mu minus lambda. What you'll notice is that as rho goes to 1, the bottom of this fraction gets closer and closer to 0. The number of people in your system goes off towards infinity. Okay. Similarly, you can think of as lambda gets closer to mu, the bottom of this fraction goes to 0. The overall fraction gets very, very large. LQ is the number of people in your queue. So excluding those in service, which at most there's one person in service when you have a one server system. And that's given by this here. And again, you can see as lambda gets closest to mu, the number of people in the queue kind of goes off towards infinity, gets very large. Another interesting result is that the total wait time, both in service and combining queue wait time and service wait time, is exponentially distributed with rate mu minus lambda. And so if mu is a lot bigger than lambda, then you're going to have a large rate, which means a small wait time. But if lambda is closer to mu, you get a rate close to 0, which means a large wait time. So the average wait time is the reciprocal of the rate. And so if this rate is small, you're going to have a large wait time. Now, that's for a one server system. For multiple server systems, the algebra gets a lot worse. You can look up formulas in the book. He provides some of them. But what I will show you is maybe more useful than that is just sort of a diagram of what happens as the utilization rate and the number of servers changes. And so that's this image from the textbook. And here, maybe I'll move my face to the other side. So this is for an MMS system, so exponential arrivals and service times, but varying numbers of servers. And so each of these lines represents a different number of servers. Along the x-axis is the utilization factor, which is going to be the arrival rate divided by the overall service rate, which is S times the S, which is the number of servers times the individual service rate. And the vertical axis is the steady state number of people in the system. So that's L. And notice that it's on log scale. So it goes 1, 10, 100. And so kind of logarithmically scaled there. And so we can kind of see with one server how this changes as we change our utilization factor. Notice that no matter how many servers we have, as our utilization factor goes to 1, the number of people in the system kind of blows up. Okay, it gets very, very large. We can notice that sort of as we increase the number of servers, it appears like more people in the system, which is not a good thing, right? We in general want to reduce the number of people in the system and the waiting time in the system. But what I'll point out is that as you increase the number of servers, S also is in the bottom of the utilization factor. And so as you increase the number of servers, yes, you move to a different line, but you'll also move to the left in this diagram. And so maybe I'll give you an example. Let's say you're at 1 server and your utilization factor is 0.8. Then you'd sort of be up on this line, and at 0.8, I'll kind of bring that over here. And that's somewhere between these two lines. And if this is 1, then this is 2, 3, 4. So this is between 3 to 4 people in your queue or in your system at any time. Okay. Now, if you add another server, you'll move up to this black line, but your utilization factor will go from 0.8 down, it'll go down in half if you go from 1 to 2 servers down here. And so your utilization rate will go down to 0.4, and you'll be way down here, and you'll expect an average of only about 1 person in your queuing system on average. Okay, so you went from 3 to 4 down to 1 person in your system by going from 1 server to 2 servers. Okay, and so in general, as you add more servers, you move to a different line, but you'll also move further to the left. Okay, yeah, so kind of you can kind of think about and kind of maybe choose a design point on this curve by thinking about how many servers do you want. And then if you know the other characteristics of arrival rate and service rate, then you can kind of work out where you'd be. And if you change the number of servers, where would you end up? And that really is the big question that you have when you're designing a queuing system is how many servers should the system have? How many is enough is really the big question. And it boils down to usually a balancing of 2 costs. Service costs, which is proportional to the number of servers. And so you kind of assume that each additional server gets paid the same as the rest or approximately equal. And so your service costs are proportional to the number of servers, but then usually you account for some level of waiting costs that's proportional to either the number of people in the system or the waiting time in the system. And so either one of those can be used to kind of calculate a waiting cost. And usually there's a sweet spot when it comes to balancing those two. So this is another figure from your textbook. As you increase the number of servers, the service cost sort of increases linearly. The waiting cost decreases as you increase the number of servers, but it's usually not linearly. It usually kind of flattens out, and that you get less gain from each additional server because there's a decent chance that that extra server is idle at least part of the time. Okay. When you add these two together, you tend to get a curve that looks something like this. Where if you have too few servers, you're going to have very high waiting costs. But as you add servers, you can drastically reduce the waiting cost. But at some point, you're going to hit a minimum where as you add more servers, you don't reap enough benefit in the waiting cost as what you added with the serving cost. And so usually there's going to be an optimal number of servers that balances the service cost and waiting costs and minimizes your total cost. For the homework, I'll ask you to find the optimal number of servers. My best strategy, or kind of the standard strategy that I follow when trying to find the best number of servers, is start off with a number of servers that you think is way too little. Okay. And then slowly increase the number of servers, and you should see the total cost go down. okay? And you keep adding servers as long as the total cost goes down, and you stop adding servers once you notice that the total cost starts going up, okay? Now you might want to run the simulation a couple times at what you think are the best couple number of servers to kind of figure out what is the best. But that's a good strategy. Is start off with too few servers, increase servers until your total cost stops decreasing and starts increasing. Okay. That's it for this video and sort of designing queuing systems. Your book has a couple sections that are really good and kind of dive deeper into some of the trade-offs and decision-making process in both designing and optimizing queuing systems. But that's it for this video.